Welcome to this video, where you will see how to implement a typical PK/PD modeling workflow in Monolix 2021 on the example of warfarin PK/PD data. We will briefly go through a lot of Monolix features. If you want to find out more about the presented features, feel free to click on one of the links appearing at the top or listed in the description, which lead to videos that present features in more detail. Let's open Monolix and create a new project. Creating a project in Monolix is an easy process that is guided with the operation of a new tab for each step. The first step is the definition of the dataset. I begin by loading the dataset in Monolix. Each column needs to be assigned a type. Here they have all been assigned automatically because they have standard names in the header: ID, time, AMT for doses, DV for observations, DVID for the observation ID. There are two observation IDs, one for PK and two for PD data. Weight, sex, and age are recognized as covariates, continuous for weight and age, and categorical for sex. Of course, these types can be changed if necessary, and standard header names that are automatically recognized can be changed in settings. I can click on Accept. Before going on, let's first explore this dataset in the Plots tab. First, we see the continuous observations of plasma warfarin concentration as a spaghetti plot against time. We can check that there are no outliers. By choosing the log on the y-axis, we can already notice that a one-compartment model with linear elimination seems adequate to fit this dataset, since the terminal part of the profiles looks linear. It is possible to stratify or filter the plot using both continuous and categorical covariates. For instance, I can stratify the data by weight. By default, individuals will be sorted into groups of equal count, but groups and colors can be adjusted here. Let's also split the plot by a categorical covariate, sex. Here, it looks like weight could have an effect on the concentration of warfarin. Let's now have a look at the effect versus time. The PD is the prothrombin complex response. It is relative to the baseline as a percentage, and it is reduced by the action of warfarin. We can also display the effect with respect to the concentration in order to have an idea on how to model the interaction between the PD and the PK part. I can see a loop for some individuals, for instance ID 14, so there is a delay between the PK and PD. We could try a turnover model or a model with an effect compartment. Finally, it is possible to display covariates to check for correlations. On the diagonal, I see the distributions of the covariates in the population, and the other subplots show correlations between covariates. Here I can, for instance, see the different weight distributions for female and male subjects, and here the obvious correlation between sex and weight. To summarize, exploring the dataset suggested using a one-compartment model with linear elimination for the PK part of the data, an indirect model for the PD part of the data. We will first focus on modeling the PK part. For this, let's go to the Structural Model tab. To define a structural model, I can browse an existing model file, load a model from the library, or write a new model with the editor. In this example, I am going to pick a model from the PK library. As seen in the data exploration, we'll first try a model with oral administration, no delay, a first-order absorption, one compartment, and a linear elimination. Two equivalent models are available, parameterized with the clearance or with the elimination constant. Let's choose the model parameterized with clearance. The next step is to choose initial estimates for the population values of these three parameters, such that the population predictions in red roughly fit the individual data in blue. The goal here is to start from a point not too far from the solution to speed up the estimation. I can either choose a value myself or use the handy Auto Init button and let Monolix find good initial estimates. I'm happy with the values, so I accept them with Set as Initial Values. The Statistical Model and Tasks tab can then be used to run some tasks to evaluate the full model and adjust the statistical model, composed of the observation model in the middle and the individual model on the bottom. The observation model relates the prediction to the observations with the residual error model. The default error model is a combined model whose formula can be displayed by clicking on this button. There is an additive and a proportional term. The default individual models include log-normal distributions for all parameters. In the middle, random effects can be removed or added to parameters. On the right, it is possible to define correlations between parameters or covariate effects. For now, let's keep this empty. As a first step, we aim at validating the structural model, therefore we first keep the default statistical model. My model is now ready for estimation. Before running, I'm going to save my project as a text file that contains all the information in the project, with an Monolix run extension. Saving a project before running is important, because when I run some tasks, the results of the tasks will then be saved in a folder next to the project file. I'm going to run and explain each of these tasks one by one. The first task estimates the population parameters with the SAEM algorithm. On this pop-up, we see how the parameter estimates evolve over the iterations of the algorithm. The algorithm works in two phases. Before the red line, the parameter space is explored during the first phase. When the exploration converges, there is an automatic criteria to switch to the second phase to stabilize towards the minimum. The results of the estimation are now available in the tab Results. Then I can estimate the empirical Bayesian estimates, or EBEs, which are the most likely parameters for each individual, or in other words, modes of the individual conditional distributions. Estimated individual parameters for each individual are shown here, and a summary of the results is displayed here. The next task estimates each individual's conditional distribution by sampling a set of values from the distribution with a Markov chain Monte Carlo procedure. This conditional distribution represents the uncertainty on the individual parameters for each individual. Estimated means of the conditional distribution for each individual are shown here, and a summary of the results is displayed here. The results of this task are used to perform statistical tests to check for potential covariates and correlations between random effects. They are also used to increase the performance of model diagnosis, particularly to help to avoid the misdiagnosis caused by the shrinkage phenomenon that can affect EBEs. I can now estimate the standard errors of the population parameters. If the model is complex, linearization method can be used to reduce the computation time, but here I will use the exact model. Standard errors are then computed with stochastic approximation of the Fisher information matrix. The correlation matrix of the estimates is now displayed here, and standard errors can also be found in the table of the population parameters. Standard errors represent the confidence on the estimated population parameters. The algorithm SAEM does not require to compute the log likelihood explicitly, so the next task allows you to estimate for the comparison of this model to more complex models later on. It can be computed either via linearization, the faster method, or via importance sampling, which is more precise. The result is displayed here along with other information criteria, AIC, BIC, and corrected BIC. Finally, I can generate diagnostic plots to assess the quality of the model. They now appear in the tab Plots. Let's take a look at plots. The observations versus predictions plot, I can choose a log-log scale to focus on the low observations. I notice that several observations are overpredicted. Let's highlight individual 12 and check his individual fits plot. By zooming in, we can see that the early concentrations are overpredicted. And we can see that it is the case for several individuals. This suggests adding a delay for the absorption in the model. I will choose a new model from the library, but before that I can set the estimated values of the last run as initial estimates for the next run by going to the Initial Estimates tab and choosing Use Less Estimates. I can then go to the Structural Model tab to choose another model. To use the model I want, I just need to change the delay section and select the model. Since this will be a new run, I will save it with a new name. Now that I've explained all the tasks, I can run all in a row by selecting them, saving the file, and clicking on Run Scenario. Again, a pop-up window allows me to easily track the progress of each task. Once the plots have been generated, I can check that the overpredictions on the plots of observations versus predictions are gone. There is no longer any clear misspecification. Let's now look at diagnostic plots to adjust the statistical model. On the plot of individual parameters versus covariates, the transformed parameters in Gaussian space are plotted against the covariate values. This is useful to see correlations between parameters and covariates and identify covariate effects. Notice that the individual estimates that are used here are sampled from the conditional distributions, instead of taking the EBEs. Here, we can see correlations between logarithm of volume of distribution and weight, as well as sex, between logarithm of clearance and weight, and a small correlation between logarithm of clearance and age. Moreover, the detailed statistical tests for correlations between random effects and covariates are available in the results, in the tab Tests. We can see from the p-values that there are two significant correlations between weight and volume of distribution and between sex and volume of distribution. Let's first add an effect of weight on volume of distribution in the statistical model. Before doing this, let's keep the estimates from the previous run as initial values for the next one. I can now add the covariate effect here. Let's display the formulas of the individual model to see how it will be affected. This added linearly the variable weight to volume of distribution in the transformed parameter space, with a new parameter beta VWT. However, I would prefer a power law relationship between the volume of distribution and weight, and I would like to center weight around its mean. This means that I have to transform weight. By clicking here, I can add a log transformed weight as a new covariate. The weight will be divided by the adjusted mean, but the value can be changed by editing here. I can now use transformed weight instead of weight. You can see now that taking the exponential of this formula will recover the usual formula using the power law, because transformed weight is the log of weight centered by the mean. Let's save this new project and then run all the tasks to estimate the parameters. For weight and clearance, parameters do not change much, because they have already been estimated before. The new parameter beta VTWT has been estimated. A wall test has also been computed with the p-value displayed here. It is low, which means that it confirms that the parameter beta is significantly different from 0. Moreover, the value of omega v has decreased, because some of the variability of v across the population is now explained by weight. In the plots of individual parameters versus covariates, I can choose the random effects to check if we have remaining correlations between the random effects and the covariates. You can see that there is no more correlation between volume of distribution and weight, and also between volume of distribution and sex. This is because weight and sex are strongly correlated, as we have seen previously. There are some other possible covariate relationships that might be worth exploring, but for the purposes of this video, we will stop here. Finally, I can check possible correlations between pairs of random effects on the plot correlation between random effects. The correlation coefficients are available by clicking on Information, and the associated p-values are also displayed in the statistical tests in results. Here, no correlation is significant. I will now compare the projects I ran, and the easiest way to compare them is to use Sycomore. I will open the Sycomore application, load the folder in which we saved our project, and I can then select the projects that we want to compare and compare differences directly in the table on the right. We can see that the BICC value has decreased after changing the structural model, and then again after adding the covariate effect. Since our last run has the lowest BICC value, let's open it again in Monolix and check the visual predictive check plot. The goal of this plot is to compare the empirical percentiles that come from the dataset to the prediction intervals for simulated percentiles that come from the model. Here there are almost no discrepancies, which means that the prediction power of my model is high with respect to this dataset. I will now take care of the PD part of the model. I will use less estimates and fix them all, and choose a PK-PD model from the library. This is a so-called intermediate approach, where PK parameters won't be re-estimated. For the PK part of the data, I will select the same model as the previous one. Since the bivariate data viewer gave us the impression that the relationship between PK and PD is indirect, let's try to model the data with the turnover indirect model. Drug is acting inhibitory, and I will choose a model without sigmoidicity. We'll go back to the Structural Model tab to make sure that observations are mapped correctly to output variables. And here, that is true. Observation ID 1, PK data, is mapped to plasma concentration in the model, and observation ID 2, PD data, is mapped to response. I'm reminding you that you can write your own models in Monolix using the MLX run language. On the library model file on the left, you can see the structure of model files, and, for example, how to use MLX run functions called macros, and how to write ordinary differential equations. I will run auto-init to get initial estimates for the PD model and save the file before running. I will run the model. As we can see from the individual fits and observations versus prediction plot, both in linear and log-log scale, there are no clear misspecifications of the model. Since there are a lot of different parameters in the PK-PD model, I will use the Monolix automated model building feature to build the covariate part of the statistical model. I will search for possible covariate relationships for both PK and PD, so I first need to unfix PK parameters. I will now go to the automated covariate search menu and use a covariate model building strategy called COSAC, selected by default, which chooses which parameter covariate relationships to test based on statistical tests. Let's say I'm sure that I want to use power law relationship for covariate weight. I can then deselect weight from list of covariates and use only log transformed weight. Let's save the project before running the covariate search. Since automated model building procedures can take quite a while to run, I will skip the estimation and show you the results directly. The COSAC iteration which produced the best results is the one on top, highlighted in blue. It contains log transformed weight as a covariate on volume of distribution and clearance, and age as a covariate on clearance and K out. Let's export this COSAC run. Generate the plots, and take a look at VPC for the PD part of the data. Since there are no large discrepancies on this plot, I can use this model for simulations further on. In conclusion, I've used Monolix interactive plots for the data exploration step to understand the data better and get insight about the possible model and effects of covariates. To optimize the structural model of both PK and PD data, I used built-in library models, interactive diagnostic plots, and Sycamore. This allowed me to easily and efficiently assess and compare different models. AutoInit and the SAEM algorithm allowed me to quickly get to stable estimations. Interactive plots have also helped me to optimize the statistical model, in addition to statistical tests performed by Monolix and automatic model building tools. The variety of features used in this process gave me flexibility and different perspectives to deal with both simple and complex problems. In another video, we used this model to show a typical simulation workflow in Monolix. You can access this video by clicking here.